Hello guys, this is CodeNCode and this is the fifth lecture of this query on trees lecture series. And in this lecture we are going to see how we would implement Moore's algorithm on path queries. We have already seen how to apply Moore's algorithm on subtree queries. Now this is time for path queries. If you haven't seen the previous lecture where I have already explained how path query works on Moore's algorithm, so just make sure you have watched that lecture before continuing to this lecture. So the problem that we are taking here is a little bit easy than the problem that we have already solved from Codeforces for subset queries. For subtree queries. In this problem we are given a tree and there are each vertex is having certain value. Then there are q queries. Each query is of the form a, b and c, and we have to tell whether there exists a vertex on path from a to b such that the value on that vertex is equals to c. If yes, then we would print find, otherwise we would print not find. So we see there are 10 to the power 5 number of nodes and queries can be as large as 2 into 10 to the power 5. The value c can be from 0 to n inclusive. So if you take a look at the example given in the problem, there are 5 nodes and 5 queries. Each node, this is the value of each node. Node 1 is having value 1, 2 is having value 2 and so on till 5. 1 is connected to 2, 1 is connected, these are 4 edges because a tree which is having n nodes has n minus 1 edges. So these are 4 edges. First n values would be given there, then there would be n minus 1 edges. After that q queries. So 1 is connected to 2, 1 is connected to 3 and so on. This is the structure of the tree and these are the value of each node. So the first query says 2, 3 and 4, which means if there is a node on path from 2 to 3 which is having value 4. If we see the path from 2 to 3 is this and there is no node which is having value 4, that is why we are printing not find. For the last 4, 5, 3, on the path from 4 to 5 or 5 to 4, there exists a node which is having value 3, that is why we are printing 5. So this is the problem as explained in the previous lecture. If I show you the code, first of all, important thing about the problem, the worst thing about, not worst thing, but there is a problematic thing about SPOJ is that it doesn't tell you about test cases sometimes. So I thought, okay, I looked at the example test case and thought, okay, there is only a single test case, but that is not true. There are more than one test cases, so we need to take care of that. I thought, okay, there is only a single test case, and I submitted for the same and you can see what happened. 5 wrong answers. So there are more than one test cases, and if you are reading a SPOJ problem, if you find EOF anywhere, it is important to look or give certain importance to this line, because it says there are multiple test cases and end by EOF. EOF is end of line. So there are no indication of how many test cases are there, so you would reach till you reach the end of the test file, that is till you reach EOF. So important thing was that there are more than one test cases. So let's go and solve the problem. To solve the problem, as explained earlier, there are as explained in the previous lecture, there are 2 types of query. Okay, so let me show you what are these things. So first of all, query structure would change a little bit, because in the previous lectures all we needed LR for each query and the index, but now since each query also have a special integer with it, that is why we are also having C field and also LCA field, because if the query is of second type, then you need to take care of LCA separately, because LCA does not lie on the path from terminating time of A to starting time of B. That is why we need to take care of LCA as well. That is why the query structure contains all these 5 fields. This is of course starting time, terminating time and flattened tree arrays. This is a timer that we would use to construct all these 3 things. We have an array for calculating LCA. We are using since we need to calculate LCA, we are using binary lifting. This is value of each node. This would be the answer of each query. This would store the answer of each query. This is level of each node in the tree. This is first this is node frequency, because we know, as explained in the previous lecture, in the range L to R, if a node appears 2 times, that means it is not a part of the path from A to B. If node appears 1 time, that means it is the part of path from A to B. That is why we need to keep the frequency. When frequency becomes 1, we would add it to the result. If frequency is not 1, or if frequency becomes 2 or 0, we would remove it. This is frequency of element. Element means the value of each node. We see each node is having certain value, so ELEF, which is element frequency, is the array to store the frequency of the values which is each vertex having. So these are the arrays. First thing what you would do, first important thing is that, of course, we are given n number of nodes, q number of queries, each time a, b and c are given, and t indicates the test case. Since the test case are not given, t is not specifically specified, that is why we need to run till we reach EOF, that is end of file. Now since you are using C++, what you can do, since each test case starts with n, right, each test case would start with this line, n and q. So what you can do, in the while loop you can put scene n. If there is no n to read, that is you have reached end of file, this won't run, and hence there is no need to take care of EOF separately. You can simply write in while loop, you can read n. So after that, I'll for now just ignore this. After reading n, we would read q, of course. After that, there are you need to initialize everything, because from the previous test case, some array or some arrays may contain values from previous test case. So what I'm doing here, I'm simply clearing all of the fields. So this is AR is actually vector to store adjacency list. So I'm clearing the vector from 0 to n. Element frequency is being initialized to 0. All of the element frequency, all of the node frequencies are being initialized to 0. Now all of the result is being initialized with 0 as well. So basically clearing all of the fields. After that, we would read n values. Now we have already taken input n and q. After that, we would read n values, value of each node, and then we would go for edge input. So we are reading values, and then there are n-1 edges. You are reading a and b. So in the adjacency list of a, you are inserting b. In the adjacency list of b, you are inserting a. After that, we would initialize timer to be 1, and also the LCA array would be initialized with -1. After that, you would make a DFS call to root, passing -1 as its parent and level to be 0. Now since we are using LCA, that is why we would initialize everything in the DFS array, in the DFS function. So the level of current node is LVL, which is already passed, so all you have to do is simply save it. The parent of current node, so the 2 raised to power 0 parent of current node is parent, of course. I've already explained most of the things. In fact, all of the things I have already explained in the previous video, previous lectures in different courses. So I'm not going into the details of that. I've already explained how this LCA array works, how binary lifting works. So that is how you calculate LCA and login time. And I have also explained we are calculating flattened tree. This is the flattened tree, and this is storing the starting time, and this is storing the terminating time of each node. After that, this is simply we are traversing the adjacency list of current node, and if the child is not equal to parent, we are making recursive DFS call to that node, passing current node as its parent, and level of that node would be 1 level above, deeper than the current level. That is why level would be passed as LVL plus 1. So in this DFS, what we are doing, we are calculating the flattened array, also initializing the starting and terminating time of the node, also calculating level so that it helps in calculating LCA, and also initializing the LCA parent. After that, after the DFS called, we would initialize the LCA array in the init function. This is somewhere here. Again, already explained this in the binary lifting video, so not going to explain it. After that, what you would do, we would read Q queries. So each query is of the form of A, B, and C, of course. So remember, as explained in the previous lecture, lecture 4 of the same series, starting time of A should be smaller than the starting time of B, because we are assuming A to be the source and B to be destination. If starting time of A is not smaller than starting time of B, of course we would swap these two values. After that, you would calculate LCA. This get LCA function is again the function that gets you the LCA between two nodes, and we are using binary lifting, which I have already explained. So we are getting LCA. So query 1, first type of query is that in which the LCA is equals to the source. If that's the case, then L is equals to starting time of A, R is equals to starting time of B, and LCA I'm setting to -1, because in the first type of query, in the range L to R, your LCA already exists. That is why we do not need to take care of LCA separately. That is why LCA I'm setting to be -1, which would later indicate that this query is of first type. If this condition is not true, that we would then we would go to else. L would be terminating time of A, as explained in the 4th lecture, and R would be starting time of B. And LCA, of course, I'm setting to LCA, which would indicate this is second type of query. If LCA is equals to -1, then it indicates this is first type of query, otherwise this is second type of query. After that, we would sort the query array using the comparator operator, using the comparator function. And here simply I'm using the first type of comparator, where we do not check for the parity of blocks in which the queries lies. So X is the block in which the first query lies, left pointer of first query lies. Y is of course the block in which the left pointer of second query lies. If they do not lie in the same block, then we would sort them by block, otherwise we would sort them by their right pointer. After sorting all of the queries, of course we would do what we do in Moore's algorithm. We would initialize the left to be 1, right to be 0, and then for each query we are taking its left, right, C, LCA and index. After that, these are the standard 4 loops that we run in Moore's algorithm. The important thing to note here is only add and remove function, how these works. So let's go and have a look at add and remove function. First, we pass index of the node to be added from the flattened tree. The index is passed from the flattened tree. So the node at current index is from we would get what node it is and then increment its frequency. When you are incrementing the frequency would become, the node frequency would become either 1 or 2. Reason, in flattened tree, each node would appear exactly 2 times. So at max, after adding, the frequency of node can be at max 2, because there are only 2 appearances of each node. So the frequency of each node would either be 1 or 2. When the frequency of node when the frequency of the node becomes 1, which means this node lies on the path from A to B. This is the part of our answer. If that happens, then we would take the value of the current node and then increment the frequency of this value. So what we are doing, suppose we were running a loop from L to R, and then we asked to add 3. Add 3 is having value 3. So what we would do, we would take that value, node 3 is having value 3, so this is the value of that node, and then in the element frequency we would increment the frequency of it. If the node frequency becomes 2, that is you are coming to else part. If the node frequency becomes 2, that means this is not part of our solution, because already explained in the previous lecture, if a node from L to R appears 2 times, that is this is not the part of our solution. That is, if frequency becomes 2, that means we need to remove this node, because when its frequency became 1 we added it, but now its frequency has become 2, which means we have to remove it because this is not part of our solution. That is why we would take the value of this node and remove decrement the frequency of this value C, because this is not the part of our solution. So we would decrement the frequency of this value. Similarly, for remove node, of what you would do, you would take out the node from the flattened tree array, and you would remove the frequency or decrease the frequency of current node. When you are decreasing the frequency would become either 1 or 0, because you would remove the node only after you have at least added one time. So you won't remove the node if you haven't added the node already, right? So the frequency would become either 2, because the frequency would become either 1 or 0, because the max frequency a node can have is 2 after adding, or 1. That is, so if it becomes 1 and after removal it could, if the frequency was 2, after decrementing it either become 1 or 0. So if the node frequency becomes 1, of course from L to R this node is appearing one time, which means this is part of our solution. If that is happening, then we would take out C and increment its frequency in the element frequency array. Because this is appearing one time, again because this is appearing one time in L to R, frequency became 1, which means it is appearing one time in L to R, which means this is part of our solution. That is why we would increment the frequency. Otherwise, if the frequency becomes 0, of course this is not the part of our solution, so we would decrement the frequency. Now this frequency is which would help us determine whether we would print find or we would print not find. So after performing all of these things, after adding after adding and removing while performing these 4 while loops, which means our ML and MR actually is equals to L and R. So we have added and removed all of the node that we needed to add or remove to get the answer of this range L to R. After that, we would see whether the element, since for this query we have to check whether there exists a node which is having value C on it. If there is a node which is having value C on it, then element frequency of C would be at least 1. So if element frequency of C is greater than 0, that means the answer we would set to 1. 1 means we have to print find. 0 means we would print not find. So if element frequency of value C is greater than 0, that means in the range L to R there exists a node which is having value C. Otherwise, if it is second type of query, this would be performed for this check. We would check this if condition. We would check for both type of queries, either it is for query 1 or 2, because L to R all of the nodes which are appearing one time would make this frequency, we would contribute something into the frequency array. If some node is having value C, then that node might have incremented the frequency C in the frequency array. So if it is greater than 0, of course the answer is 1. Otherwise, if it is second type of query, that means LCA is not equal to -1. LCA, remember that we have taken out from this query. So if LCA is not equal to -1, which means this is second type of query. If this is second type of query, that means we have to check for LCA separately. So I'm checking if the LCA contains if the value of LCA is equals to C, then of course the result of current query would be 1. After performing this for each query and saving into the result array, we would simply run a loop from 1 to q and would answer for each query. If it is 1, we would print find, otherwise we would print not find. So this was how you would solve this problem. One more thing, since there are more than one test cases, so initialize t to be 0. So if t is greater than 0, which means you are solving the t is equals to 0 means you are solving the zeroth test case. In that case you won't print and L, that is next line. The question specifically asks you to print a blank line after every test case. So that is why if t is equals to 0, which means you are on the 0 test case, so you would not print next line, otherwise increment t, and when t becomes 1 or more than 1, which means we are solving at least the first or more than first. I'm talking about zero-based indexing. So you are solving at least first test case or more than that. In that case you would print extra blank line. So that is what is happening here. So this was how we would solve this problem. Of course you would have some kind of problem in understanding this solution. There may be some problems, so I would advise you to ask on the discuss.codechef.com the article that I have created for this course separately. So if you have any query, just ask there. I'll be putting the link to the I'll be putting the link of solution into the description, so you can check the solution there. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.